Hello. In this video, we're going to look at solving non-homogeneous equations and undetermined coefficients. Okay, so the first thing we need to do is to just refresh our memories into what is a non-homogeneous equation. So a non-homogeneous equation has the following form. Y double prime plus P of T y prime plus Q of T y equals G of T. So in previous videos, we've gone through and we've solved homogeneous equations. So homogeneous equations have a similar form to this, except they have a zero on the other side of the equal sign over here. So non-homogeneous equations have a G of T instead of a zero, so that makes them a little bit more complicated. Okay, so to go through and figure out how to solve these, we're going to start off with theorem. So we'll say if y2 and y1, capital Y2 and capital Y1, are solutions of the homogeneous equation, of a non-homogeneous equation, y double prime plus P of T y prime plus Q of T y equals G of T. Then the difference is a solution of the corresponding homogeneous equation. Y double prime P of T y prime plus Q of T y equals 0. If, in addition, lowercase y1 and lowercase y2 are a fundamental set of solutions of the homogeneous equation, then capital Y1 minus capital Y2 equals C1 lowercase y1 plus C2 lowercase y2 for some C1 and C2. Okay, so there's two pieces to this theorem. The first piece says that if we have solutions to the non-homogeneous equation, then we can subtract them and get a solution to the homogeneous equation. So we'll go through and prove that. That's not necessarily obvious. And then on top of that, and this part maybe needs a little bit of explanation, right? So what is a fundamental set of solutions? Well, a fundamental set of solutions means that the Wronskian is non-zero for the two solutions. So that's what it means. So it means that the Wronskian of y1 and y2 is non-zero. And if the Wronskian is non-zero, that means that a linear combination of these two solutions will get you any solution to the homogeneous equation. So a linear combination will get us any solution. So what the second part is saying is that take the y1 minus y2, that's going to be a solution to the homogeneous, and we can go through and represent that solution as some linear combination of y1 and y2, assuming that y1 and y2 do form a fundamental set, and so that you can get any solution. So if this is a solution, then we should be able to represent it as a linear combination. If linear combination of y1 and y2 gets us all solutions, there's got to be one of them that is this solution. So that's what it's saying. Okay, so let's go through and prove that. All right, so we start off, suppose capital Y1 and capital Y2 are solutions to y double prime plus p of t y prime plus q of t y equals g of t. Okay, assuming that's the case, right, we could take y1 and plug it into this, and we would get y1 double prime minus p of t y1 prime plus q of t y1. And we could take y2 and we could plug it into this, and we would get y2 double prime plus p of t y2 prime plus q of t y2. And if we went through and subtracted those, then this one we could replace with g of t, because we know it equals g of t. And this one we could replace with g of t, because we know it also equals g of t. And we would end up getting that the difference of these two things here would be 0, right? Does that make sense? So you take y1, plug it in, that's this. Take y2, plug it in, that's this. Subtract them, and then substitute in place of this one, it equals g of t, so substitute g of t. And then in place of this one, substitute g of t, because it equals g of t. And then if you subtract the g of t's, they cancel and you get 0. Okay. So next, what we can do is we can go through and distribute this negative. We can reorder so that the primes are all next to each other. And what you'll end up with is you'll end up with y1 double prime minus y2 double prime, right? And then we're going to have minus p of t y1 prime plus p of t y2 prime plus, hey, hold on, that's supposed to be a plus, yep, little mistake there, minus, and then q of t y1 minus q of t y2 equals 0. And then we can, so we can combine these, right? So we know that derivatives distribute over addition or over subtraction. And so that means that you could go through and you could factor out derivatives over addition or subtraction as well. So we could rewrite this as y1 minus y2 double prime. And then you could factor out the p of t here and do the same thing here, and we'd get y1 minus y2 prime. Okay, and then we could do the same, well, we don't have to do any derivative stuff, but you could factor out the q of t here, and we'd get y1 minus y2 equals 0. Okay, so now take a look at this. This has the form of something double prime plus p of t something prime, that same something, plus q of t times that same something equals 0, right? That's the form y double prime plus p of t y prime plus q of t y equals 0. So that tells us that this thing that is in these spots, since when you plug it into this, it ends up equaling 0, that tells us it's a solution to the homogeneous equation. So this tells us that y1 minus y2, we could plug it into this and it would make it true. That means y1 minus 2 is a solution to the homogeneous equation. right, written right there. Okay. And then if that's a solution to the homogeneous, from there, all we have to do is to get the second part, right? This second piece is to say that since any solution to the homogeneous can be written as a linear combination of a fundamental solution set, then this one in particular certainly can. And that completes the proof. Okay, so moving on. Next thing that we need to go through and solve non-homogeneous equations is another theorem. The next theorem is the general solution of the non-homogeneous equation y double prime plus p of t y prime plus q of t y equals g of t is y equals phi of t, which equals c1 y1 plus c2 y2 plus capital Y, where lowercase y1 and lowercase y2 are a fundamental set of solutions to the corresponding homogeneous. C1 and C2 are arbitrary constants. And capital Y is a specific solution. So we're going to use the term specific solution to the non-homogeneous equation. So what does the theorem say? It says that if we want to go through and find the general solution, right? So let's recall what the general solution is. The general solution of a differential equation is the solution that represents all of the solutions, right? It's going to have, C's in it and other things like that, because it needs to represent all of the possible solutions. Okay, so that's what the general solution is it's a formula effectively that gives you all of the solutions. So the general solution, the solution that gives us all of the solutions, has this format. So it's got some C's in it. Okay, and what it is it says that it's a combination of two pieces. One here, the C1 y1 plus C2 y2, that comes from the homogeneous equation, and then two, the solution y, which is what's called a specific solution. I can't remember if we've used that term yet, but specific solution just means that it's not the general solution, it's a specific, it's a solution. like any old solution, just one solution. It's one solution that you successfully have found to the non-homogeneous equation. Okay, and so that's what the theorem says, is that you can go through and you can find the general solution by combining two pieces. One comes from the corresponding homogeneous, and two comes from a specific solution to the non-homogeneous. Okay, there's actually a very similar theorem to this if you've taken linear algebra. There's a very similar theorem in linear algebra that says this, that gives you the same idea for going through and solving matrix equations. Okay, so let's go through and prove this. All right, so we're going to start off. Suppose y equals phi of t is any solution to the non-homogeneous equation. Oh, hold on, actually, almost forgot. Suppose y equals phi of t is any solution, and y is a specific solution to the non-homogeneous equation. Y double prime, p of t p, p of t y prime, q of t y equals g of t. All right, so what we've got there is that we've got any solution. So y equals phi of t is you can think of it as a random solution. So it's a solution that we've gone through. We've grabbed just a random any old solution, and then y itself is a specific solution. So we've gone through and we've found something that we could plug in that will solve it. And so the difference between these, if you're not understanding the difference between them, is that if you think of the proof like you were doing it again and again and again, every time this y would be the same solution, and each time this y equals 5t would be a different one. So you're like generating a random solution. That's what it means why we put any in there, that it's any solution. It's not a specific one. It's just one of the infinite number of solutions that will solve the differential equation. And then meanwhile, this is the same solution every time. It's one that we've gone through and we've found that we know will work. Okay. So since this is a solution to the non-homogeneous equation, and this is a solution to the non-homogeneous equation, then due to the previous theorem, what we can do is we can go through and say, thus, phi of t minus y equals c1 y1 plus c2 y2. Right, so, okay, so where'd that come from? That came from that first theorem, right? So this first theorem where we said if y2 and y1 are solutions, then the difference is going to be a solution to the homogeneous, and we could represent the difference using the fundamental solution to the homogeneous. So phi of t is a solution to the non-homogeneous. Y is a solution to the non-homogeneous. Thus, if I subtract the two, then I can go through and represent them as a linear combination where y1 and y2 are a fundamental set to the homogeneous equation. And then all you need to do there from there is just move the y to the other side, and thus phi of t equals c1y1 plus c2y2 plus capital Y. and that completes the proof. So if you have a formula that for any solution you can go through and represent that solution, then what you've done is you've created a formula that will generate solutions. Okay, so since phi of t is any solution, thus we know that any solution can be rewritten into this format. Does that make sense, right? So any solution can be written as C1y1 plus C2y2 plus capital Y. That's what the theorem says, right? The general solution, which is the general solution is a formula for any solution, is given by this, and we're saying that any solution is given by that. So that completes the proof. All right. So the consequence, so what's the consequence of this theorem? What does it mean? It means if we want to go through and solve a non-homogeneous differential equation, if we've got a non-homogeneous differential equation, we want to solve it, then we need two things. We need to have a fundamental set of solutions to the corresponding homogeneous, and we need to have a actual solution, a specific solution to the non-homogeneous. All right, so what is the consequence? So I'm just going to write that down. To solve a non-homogeneous we need one, a fundamental set of solutions to the corresponding homogeneous. So we're going to need to solve homogeneous equations to solve non-homogeneous equations. And then two, we're going to need an actual solution, all right, an actual solution, a specific solution. So to go through and solve and find all of the solutions, the formula for the general solution, we're going to need to have one solution. So we can't find all of them unless we can find one. Right, so solving these non-homogeneous equations becomes a two-step process, 2 steps. We need to do both of these. Fortunately, we've already done this one a bunch of times, so that one should be easy. So we're going to focus on this one, on this second one. How do we go through and find a specific solution? How do we go through and find one solution to the non-homogeneous equation? All right, so what we're going to do is we're going to learn 2 methods. One method in this section is called the method of undetermined coefficients. All right, so suppose we have a differential equation, a non-homogeneous differential equation. Hold on. We're supposed to have a specific one, not a general one. Minus 3y prime minus 4y equals 3e to the 2t. Okay. And the idea is that we've got this non-homogeneous equation, and what we want to do is we want to go through and find a solution, just one. We're not trying to find all the solutions. We just want to go through and find one solution. Why? Because of what we just said, because that's what we need to do to be able to go through and to find all the solutions to a non-homogeneous. We need one solution to the non-homogeneous combined with all of the solutions for the homogeneous. All right, so how do we go through and do this? Well, so the undetermined coefficients method, another name for it could be the guess method. You just start guessing. So, we're just gonna go through and guess what could be a solution? What could potentially be a solution to this? Right? Well, if you think about what's happening here, you're taking the derivative of something and your second derivative of something, and you're combining it with the derivative of something, and you're combining it with that thing itself, and then you're getting 3e to the 2t, right? So what thing would you differentiate a bunch of times and then could potentially look like a multiple of e to the 2t? The answer, if you think about it for a few minutes, is a multiple of e to the 2t, right? So the reason it's called undetermined coefficients is because this a, it's undetermined, right? So what we're going to do is we're going to guess something, and then we're going to go through and try and solve for the coefficient that would make that guess work. Does that make sense, right? So we're going to start off with a guess, and through our guess, we're going to try and solve for what the a would need to be, so that if we plugged it in, it would make this equation true. And if at the end of this we make the equation true, then that's what we're looking to do. We've got a solution. We've got something that you could plug in that would make this work. Once we have one thing that we can plug in and make it work, then we can go through and find others. All right. So y prime, you're going to get 2a e to the 2t. Y double prime, you're going to get 4a e to the 2t. We've got definitions for y prime, and y double prime. Take them, plug them in. You're going to get 4a e to the 2t minus 3 times 2a e to the 2t minus 4 times a e to the 2t. And this still equals 3e to the 2t. Just taking these things and plugging them in, rewriting it. And if we do that, you'll get 4a e to the 2t minus 6a e to the 2t minus 4a e to the 2t equals 3 e to the 2t. And then, these are going to cancel. So we'll get minus 6a e to the 2t equals 3 e to the 2t. We could divide both sides by e to the 2t and cancel those. And then if you divide, you're going to get a equals negative 1/2. Okay. So if we go through and do these substitutions into our non-homogeneous equation, then what we end up getting is that a would have to equal negative 1/2 for those substitutions to work, to get us a solution, right? So what that means is if you took this and combined it with this, it means that y equals negative 1/2 e to the 2t is a solution to this, the non-homogeneous equation. Right? And that's what our goal was. Our goal was to do this second part, right? Was to find the specific solution. The specific solution is just one. This is not all of the solutions, to be clear. This is just one solution. This is one thing that you could plug in and that it will work. If we want to go through and find the rest, right, then we can go through and rely upon these previous theorems. And what they say is that if you go through and find a fundamental set of solutions to the corresponding homogeneous equation, we could take that fundamental set and we could combine it with the one solution that we've just found using this format, and that would get us all of the solutions to the non-homogeneous. All right, so let's just quickly do that because it's not especially difficult. Right? So if the corresponding homogeneous would be the following. To solve this, we could go through and use the characteristic equation. And then if you factor this, you'll get r minus 4, r plus 1. So we'll get r equals 4 and negative 1. And thus, the solutions to the homogeneous are going to be of the form c1 e to the 4t plus c2 e to the negative t. Okay, and then what the previous theorems say, this theorem here, what it says is it says take your solution that you just found, combine it with the solution to the homogeneous, which is defined by the fundamental set e to the 4t and e to the negative t, and then you can get the solution to the non-homogeneous. And let's write it up here so that it's close to the non-homogeneous. So you're going to get y equals c1 e to the 4t plus c2 e to the negative t minus 1/2 e to the 2t, right? Look at that. It has this format, C1y1 plus C2y2 plus the y, the specific solution that you got. That is going to solve this. That's going to be a solution. It's going to be the general solution. Okay, so let's tie it all together. There's a lot going on there, right? So we started off with this non-homogeneous. We wanted to go through and find just one solution. To find that just one, we used this method called undetermined coefficients by making a guess as far as what we thought the solution could look like to this. That guess led to these consequences. We then combined them, plugged them in. That guess enabled us to determine, oh, wait, our guess worked. We ended up getting a is -1/2. Putting that together with our guess got us a solution to the non-homogeneous, a single solution, just one of an infinite number. All right, and so that's our specific solution. And then after that, we decided, hey, let's just go through and find the general solution to this thing. The way that we do that is we go through and we find the solution to the homogeneous, and then you take the solution to the homogeneous and you combine it with the one solution you have to the non-homogeneous to get you all of the solutions to the non-homogeneous, right? And so now you could go through and do combinations of C1 and C2, and it will solve this differential equation. Anything that you get will solve this. You'll be able to just generate solutions. Okay, so if this is a sort of guess and then check method, then we need to know how to guess, right? So what was the key behind this guess, right? Anytime you see an exponential function like this, what you want to do is you want to go through and make a guess like this. You want to take multiples of that exponential function, right? And so that's kind of your first formula that you learn, is that if you see, some multiple of e to the at, then your guess is going to be a generic multiple of e to the at. Not that specific one, but a generic one. What about if you were going through and solving and you had trig functions? So what if we had y double prime plus 3y prime minus 4y equals 2 sine t? What would our guess be there? All right, so what you want to do is you want to think about it. So I'm going to take the second derivative of something, and I'm going to take the derivative of a thing, and I'm going to combine it with that thing, and I need to get sine function. All right, so what do you differentiate that gets you sine? Well, the derivative of cosine is negative sine, right? So you could have cosines that you could differentiate. What's the second derivative of something that would get you something that looks like sine? Well, isn't the second derivative of sine something that looks like sine? So what you've got is you've got a combination of sines and cosines in your guess. And that's because these are the things whose first and second derivative could end up looking like sine of t. So that's why you guess them. So hopefully that makes sense, right? So, and then from there, what you want to do is the same thing we did in the last one. You want to figure out, okay, what are the consequences of my guess? I'm going to get a cosine t, and then minus b sine t, and then y double prime. I will get negative a sine t minus b cosine t. And then I could take these three things, plug them into the non-homogeneous. You're going to get negative a sine t minus b cosine t minus 3a cosine t minus b sine t minus 4a sine t plus b cosine t. And we want that to equal to sine t. Okay, so you could go through and distribute these out. Negative a sine t, b cosine t, minus 3a cosine t, plus 3b sine t, minus 4a sine t, minus 4b cosine t, equals 2 sine t. And then we could go through and group these based upon coefficients of sine, right? So we're going to have negative a as a multiple of sine, plus 3b as a multiple of sine, minus 4a is a multiple of sine. And then we could do the same thing for b. We've got negative b minus 3a minus 4b cosine. Okay, and then we could go through and combine these. So looks like we're going to have minus 5a plus 3b sine t. And then over here, let's reorder these so that we've got a first. We'll have negative 3a minus 5b cosine t. And then what you can do here is, so we don't have any cosines, but what that means is you could put just a plus 0 cosine t over here. And then so you can set the coefficients equal. So the coefficient of sine needs to be the coefficient of sine. Coefficient of cosine needs to be the coefficient of cosine. So we get minus 5a plus 3b equals 2, minus 3a minus 5b equals 0. And then we could go through and solve this, multiply this top one by 5 and the bottom one by 3. So we'll get negative 25a plus 15b equals 10. And the bottom one by 3, we'll get negative 9a minus 15b equals 0. And then if we go through and add these, we'll get negative 34a equals 10. A equals 10 over negative 34. Right, so we're going to get negative 5/17. And then I'm running out of space here. So take negative 5/17, plug it into this equation, and you can go through and solve for b as well. So b is going to equal, you should get negative 3/17. Taking those two, let's go up here and around, and plugging them back in with this original, we get y equals negative 5/17 sine t minus 3/17 cosine t. So that is going to be my specific solution to the non-homogeneous. So that's something I could plug in that would work, but it's only one solution. That's not all the solutions. That's just one. And so this is our specific solution. Let's just be clear here. Label it specific. Okay, and then if we wanted the general solution, what would the general solution be to this non-homogeneous equation? Well, we would take the specific and combine it with a fundamental set from the homogeneous, or with, if you want to think about it, or with the homogeneous solution, right? So what was the homogeneous solution? It was this. And so you could just take the homogeneous solution and you just combine it with the specific solution. So we just take that and just copy it, right? So we got C1y1 plus C2y2, and you know what? I don't have enough space here, so just take this and put it here, and that's going to be the general solution. Okay, so that's how it works. Take homogeneous, combine with the one solution that you end up finding through the undetermined coefficient method, and you've got all of the solutions. You can generate all of the solutions now to the non-homogeneous. Okay, how about if we had y double prime minus 3y prime plus 4y equals 4t squared minus 1. So this time we have a polynomial. Okay, and so for a polynomial, we can go through and our guess for a polynomial, and this is a little bit of experience, because if you just went through and looked at this and said, okay, well, what second derivative could I have that would look like 4t squared? So you'd think that you'd have to go all the way up to t to the fourth, right? Because the second derivative of t to the fourth would get you t squared. But you don't need to do that. You only need to go up to a polynomial that's the same degree as the polynomial that's represented here for g of t. And so we can just use AT squared plus BT plus C. And then you can do y prime equals 2AT plus B. And then y double prime equals 2A. And then you can take those and plug them in. Let's see here. What solution did we end up getting? I'm just going to skip ahead, so you can go ahead and try that and check it out and see if this is what you get. But according to my notes, I got A equals -1, B equals 3/2, and then C equals -11/8. All right, so taking those and plugging them in, combining these, we're going to get y equals -t squared plus 3/2 t minus 11/8. So that's going to be a specific solution. That's just one, right? That's our specific solution. And then the general solution then would be, using our solution from the previous page, C1 e to the 4t plus C2 e to the -t, and then plus the specific solution that we just generated. You just pop it right in there, and then that will get you the general solution to the non-homogeneous. Okay, so just a quick little rundown on our guesses, right? So what should your default guess be? So I went through and created like a little mini table. Here's G of t. Here's your guess. So if G of t has e to the at, right? And there could be a coefficient in front of that, but if it has e to the at, then your guess should be y equals capital A e to the at. Right? If you've got a combination of A sine t plus B cosine t, and note, this could include if A is 0, you could just have cosines, or if B is 0, you could just have sines, or you could have both if A and B are non-zero, right? So you could have both. Then your guess should be capital A sine t plus capital B cosine t. All right. What if you have a polynomial an tn plus an minus 1 tn minus 1 plus dot 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 plus a0? If you've got a polynomial, then you should guess a polynomial, and your guess should be the same degree as the original. Okay, so those are the examples that we've covered thus far. All right, so what if you have something that's more complicated than these things? All right, so what you could have is you could have things that are a product of two of these, right? So if you have combinations that are a product of two of these, then what does your guess look like, right? So if you have a product, right? So what's an example if we had a product of functions? So if we had y double prime minus 3y prime minus 4y equals -8 e to the t cosine 2t. What do you do then, right? Okay, so if we had this, what would our guess be? All right, so what you can do if in this case is you could combine two of the possibilities, right? So for the exponential, we know to guess something that looks like this. For the trig, we know to guess something that looks like this. So just combine them, right? So if you combine them, what would that look like? It would look like a e to the t cosine. Well, so let's start with sine. Sine 2t plus b e to the t cosine 2t, right? So we combined two of them. So when you have trig, you have sine t and cosine t, you need both. And then when you have exponentials, you have e to the at, so you just put the two together. Okay, so since there's a product here, we just put combinations that look like that. All right, what about sums of functions or differences? Right, so for example, what if we had y double prime minus 3y prime minus 4y equals 3e to the 2t plus 2 sine t minus 8e to the t cosine 2t. What if we had all three of the previous cases that we've looked at? Okay. Well, what you can do is you can solve them separately and then combine the solutions. Okay. I think that's the easiest way to go through and do this, right? So what you can do is you can solve separately, then combine the solutions. What do I mean by solve separately? I mean, go through and split these up. So go through and solve y double prime minus 3y prime. I mean by solve by find a specific solution. Then when you're done with that one, go through and do y double prime minus 3y prime minus 4y equals 2 sine t. Then when you're done with that one, because, oh yeah, this problem's only going to take 5 minutes, right? Equals negative 8 e to the t cosine t 2t, right? So solve this one, you'll get y1. Solve this one, you get y2. Solve this one, you get y3. And then thus the solution that will work for all of these will be capital Y equals y1 plus y2 plus y3. All right, so if you've got the solution for this one and for this one and for this one, if you add them up, the sum of the three, if you plug it in, it will solve all three at the same time. So that's how you can go through and handle sums of functions, is by just solving for each piece separately. And then when you're done, combine them and you'll get the specific solution for the sum or difference. Okay. Finally, the last thing that we're going to look at is what if a gas does not work? All right, so what might that look like? How's that possible? All right, so if we have y double prime minus 3y prime minus 4y equals 2e to the negative t. All right, so you start off, innocently enough, you're like, oh, piece of cake, I got this. I know how to do these. I'll do y equals a e to the negative t. Then y prime will be negative a e to the negative t. Then y double prime will be a e to the negative t again. Then I take them and I plug them in, and I get a e to the negative t minus 3 times negative a e to the negative t minus 4 times a e to the negative t equals 2e to the negative t. And I go through to solve this, right? And what happens? I'm going to get a, and then I'm going to have plus 3a, then minus 4a, all times e to the negative t equals 2e to the negative t. Here I get 0 e to the negative t equals 2e to the negative t, and uh-oh, no solution. All right, no solution. Didn't work. The method broke, right? So does that mean that there's no specific solution to this? No. It does not mean that at all. It just means that there's no solution of this form. The guess that we made didn't work. All right, so what it's saying is that a constant multiple of e to the negative t was not a solution to this. Okay, and actually, if you go through and look at the solution to the homogeneous, if we recall we've written it down a bunch of times, but what is the solution to the homogeneous? It's c1 e to the 4t plus c2 e to the negative t. Look at that. Can a constant multiple of e to the negative t, can that go through and be a solution to the non-homogeneous when it's already a solution to the homogeneous? That doesn't really make sense. Okay, so since it's a solution to the homogeneous, right? That tells us that if you take this and plug it into the left-hand side here, we're going to get 0, because that's what it means to be a solution to the homogeneous. So since it's going to be 0 on the left-hand side, it can't possibly be 2e to the negative t. So because of that, this actually was not a great guess. But, that's okay if you didn't catch that. It's okay to just go through and do this, plug in, and then get to the end here and get no solution. Now, what do we do next, right? So because it wasn't a solution, because a constant multiple didn't work, what's our next step? Well, next step is to try a different guess. Okay, we still want to try things that look like exponential functions. So we just determined that a constant multiple did not work. If you recall from earlier videos, right, when we were going through and we were trying to find an additional solution when we only had a constant multiple, what we ended up doing was we ended up adding a t in here, right? Because t e to the negative t is going to have derivatives that look like this. So if you use the product rule on that, you're going to have derivatives that are going to be a constant multiple, e to the negative t. So adding a t will enable us to go through and still, maybe generate solutions that could work. Okay. And in order just to cover all the bases, you could just put a t in here and then try it. But what I prefer to do for my second guess, if the first guess doesn't work, I prefer to go through and do y equals at plus b times e to the negative t. I prefer to do a linear multiple, right? So this is a constant multiple because you're just putting one number times e to the negative t. So we're going through and now we're doing a linear multiple where you've got a linear term here. And then if the linear term doesn't work, you could always go through and try a quadratic multiple. Okay, and that's the most that you would need to do. When would that occur? If the left-hand side here were in the form of a repeated root, then that means that the constant multiple and the linear multiple are both going to be homogeneous solutions. So they can't possibly be non-homogeneous solutions. So in that case, if you guess the constant multiple that's in the homogeneous solutions, it's not going to work. And then if you go to the linear multiple, it's not going to work either. And so you're going to have to go all the way to the quadratic multiple. So that's the most that could possibly happen. And that, again, if you're watching for that and you'll notice that you have a repeated root, then you could fast forward past the constant multiple and the linear multiple. But in any case, let's go through and try this and see what happens. So if you do y prime, you're going to get at plus b times negative e to the negative t, and then e to the negative t times a. And if we go through and simplify that a little bit, what's going to happen here? We're going to have something times e to the negative t. So we're going to have a negative at, and then we're going to have a negative b, and then a plus a. Okay, let's try y double prime. So we're going to have, we'll take this, negative at minus b plus a times negative e to the negative t plus e to the negative t times the derivative of this, which is going to be negative a. And we could go through and simplify that. So we're going to have something times e to the negative t. What is that something going to be? So we're going to have negative at times a negative. So we're going to be back to a positive at. We're going to have a negative b times a negative. So that's going to be a positive b. And then we're going to have a negative a and another negative a. So we'll have minus 2a. Okay, if we take all of that and plug it in, right? So what are we plugging it into? We're plugging it back into this equation here that was our original. So if we do that, what are we going to get? We're going to get at plus b minus 2a e to the negative t. So that's y double prime. And then what was the next part? So we're going to have minus 3y prime. So we're going to have minus 3 times y prime, which is negative at minus b plus a e to the negative t. And then we're going to have minus 4, right, I believe. Let's just check. Yep, minus 4 times y. So minus 4 times at plus b e to the negative t. And then that needs to equal, I believe it was 2e to the negative t. Let's just check that. Yep, 2e to the negative t. All right, and so we could go through and do some simplifying here. So we're going to have, yeah, let's just do it in 2 steps. We'll have at plus b minus 2a e to the negative t. And then here we're going to distribute this. So we're going to have plus, we'll have positive 3at, positive 3b minus 3a e to the negative t. And here we're going to have negative 4at minus 4b e to the negative t equals 2e to the negative t. All right, now at this point we could cancel all these e to the negative t's by dividing both sides by e to the negative t. And then we could do some combining here. What do we have? We have at, 3at minus 4at. Look at that, those cancel. All right, what else do we have? We have b plus 3b minus 4b. So that's 4b minus 4b. Those cancel too. Okay, and then so we have minus 2a minus 3a. So we're going to have minus 4a, and then that needs to equal 2. And so we get a equals negative 2/5. All right, and so that worked. And so we could take that, plug it back into the original here. Now, so the fact that the b's cancel, what that means is that the b's went away. That doesn't mean that the b's are 0. It means that the b term didn't matter. So we didn't need it. So technically, it would have been fine to go through and just guess a t e to the negative t, right? But we didn't know that beforehand, so we could go ahead and just try it without, with the b in there. And so what that means is that the b could be anything, and it would still work. And so we could do negative 2/5. Since the b could be anything, let's just use b equals 0. So we'll have negative 2/5 t e to the negative t. But if you wanted to, you could put a 1 in here, or a 2 in here, or a negative 5 in here. All of those will all be specific solutions to the non-homogeneous. All right, so that's going to be our specific solution. Take that, plug it in to this original guy here, and it will work, right? So that's our specific solution. And that's how you find it, right? So that's what you do if the solution doesn't work. You can go through and go from a constant multiple, a, you could step up to a linear multiple, okay? And then the general solution to this, if you wanted to go through and find the general solution, sorry, not to this, but the general solution to this non-homogeneous differential equation would be to combine the homogeneous solution with what we just found. So we'd get y equals c1y1 plus c2y2 plus that solution we just found. Just take that and pop it in over here, and that would give you the solution. Well, the y1 and the y2 are supposed to be e to the 4t and e to the negative t. I don't know why I put that instead, but maybe it's space limitations. I didn't have enough room. All right, so that concludes the video. So that describes how to go through and solve non-homogeneous equations in general. That means we've got to find a homogeneous solution and a specific solution to the non-homogeneous and combine them. And it describes one of the methods for finding that specific solution, the method of undetermined coefficients. In the next video, we will look at a second method for doing that. Okay, so that concludes the video. Thank you for watching. I'll see you next time.